Okay, everybody find a coin and toss it 10 times, and then record the number of heads that you have. All right, find your coin, toss 10 times, and say how many heads you have. All right, so we conducted a little experiment. You tossed your coins 10 times, and 1, 2, 3, 4, 5, 6, 7. I got 7 heads. We're going to go around the room, starting here. Just tell me very quickly how many heads you got. How many heads did you get? Okay, 5. How many heads? 5. We can start up front here. Okay. How many? 6.
7.
Okay. Who's next? Oh, Leanne. 5.
6.
7.
3. 7. 6.
You didn't borrow one. 7. 7. Okay, very good. All right. So looking at this, we see that the numbers bounced all over the place. In a perfect world, you would have gotten 5 heads, but that's we don't live in a perfect world. So this is interesting. We got this, but if we add these up, we've got 250 tosses here, and so I'm going to add them up very quickly. That's why I put them on this Excel spreadsheet. So we'll just add those. 142. So out of 250 tosses, that's a little high, actually. Did I do that right? That's 250 tosses, 142 heads. But if you divide that, what does that come up to? I got 25 numbers, yeah. 56.8. Okay, that's a little high. However, some studies, and I have a little newspaper article that says that the chance of getting a heads versus tail is not the same. I want to say maybe, I can't remember, one side is just a little heavier, so it tends to go down a little more. So maybe that's part of what we're seeing here. Okay, but this little experiment helps us to introduce some of the terms that we want to talk about in this chapter. One that the author did not mention is experiment. An experiment is a process that allows us to, view some outcomes. And that's what we just did. We had an experiment. We tossed coins. Okay. Once we have our little experiment, we've got our data, then we can talk about events. This would be any outcomes that can result from our experiment. Okay, we just want to understand the language that we'll be using. So we could talk about, an event being getting an even number of heads, or getting all heads or whatever. There could be lots of different events in the experiment that we conducted. However, when we break our events down so they can't be broken down into any simpler pieces, we call that a simple event. An event that can't be broken down into simpler events. Okay. Or it can't be broken down any further. For instance, let's say we were tossing 2 coins, and I was interested in the event of you getting a heads and a tail. Okay. Well, that can be broken down into On the first coin, I get a head. Second coin, I get a tail. Versus first coin, I get tail. Second coin, I get head. And in a situation where the coins are really distinct, let's say you're tossing a nickel and a dime, then that makes a difference, right? Okay, so simple events are events that we can't break down into any simpler pieces. And then we also want to talk about the sample space, which is the set of all possible, it's the set of all simple events. That's the best way to describe it. Set of all simple events. So if we go back to our example of tossing 2 coins, then our sample space, what are the possible outcomes? The sample space could be heads, 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 tail, tail, head, and then tail, tail. These are all of the possible outcomes. They've been broken down into simple events for this particular experiment. Okay, and usually when we talk about the sample space and when we look at the classical formula for probability, which we'll do in just a minute, we want to make sure we have simple events so that we can assume the events are equally likely. Okay, they're equally likely. All right, some notation. P, of course, represents probability. All right, and then our events might have names A, B, C. It could be anything. E is pretty generic for the name of an event. Okay, we talk about the probability of A. Okay, this is not multiplication. This means probability of event A. And what else was there? Or is that it? Okay, that's it. Okay, very good. So that's some of the notation that we're going to use. Oh, let's go back up and talk about this rare event rule for inferential statistics. We talked about this, I think, maybe in chapter 1, and here it is again. But basically, let's say we had an assumption when we started tossing our coins. We assumed that the likelihood of getting a heads and a tails or a tails was 1/2. It was equal, right? And from that, what we're going to learn is how to calculate the probability of getting, let's say, 5 heads when we toss 10 coins. All right, we're going to figure that out. But we've got a particular assumption. We're assuming that the probability of heads is 1/2. That's our assumption. And I would say that to get 10 heads would be a rare event. Wouldn't you agree? But let's say we were tossing our coins and we did get 10 heads. Okay? Then what might you decide? Something's wrong with really our assumption. Right? Maybe our assumption is wrong. Maybe it's not 50-50 for getting a heads versus a tail. Right? That's what this says. If we have a particular observed event, but in theory, the probability of this thing is small. But here I am holding that event in my hand. I can see it. Then there's a problem likely with my assumption. Yes? Yes. Yes, but this goes even beyond, just our coin tosses to even larger experiments. And so generally, when, under a particular assumption, like the mean of a particular population is whatever, and then we go out, we get some data, which is a little bit farther in the class, we'll talk about that. And then we find this other mean that would be unusual in a sample given our assumption. Then we decide there's something wrong with our assumption. Okay? So this is a really important principle regarding probability and statistics. Okay? Okay, identifying the sample space. Let's just quickly go through a few of these examples. Sample space is the set of all possible outcomes. And so here we have an experiment that consists of tossing a coin and then rolling a 6-sided die. So our sample space, the set of all possible outcomes, S is generally used to represent sample space. Okay, it's going to be heads 1, heads 2, heads 3, 4, 5, and 6, tails 1, tail 2, 3, 4, 5, and 6. This is the set of all possible outcomes. Okay? All right, that's all of our possible outcomes. All right, I think I already showed you the sample space for tossing 2 coins, but let me show you a different approach to coming up with that. Sometimes if you want to, you could use a tree diagram to come up with our sample space. For our first coin, we have how many outcomes possible? 2. We could either get head or tail. Okay, then from there, we got a second coin. We still have what? 2 outcomes, heads, tail. And so to come up with the sample space from this, we look at the path, we follow it to the end. And so if I go to the end of this first path, we've got heads, 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 tail, tail, head, and tail, tail. So the tree diagram is just a tool that can help us come up with the sample space. Okay, Leanne's counting. What are you counting? Oh, okay, gotcha. Okay, very good. Sometimes it's easier to start on the end and back it up to get it. Yes, I mean you might still write it left to right, but I can see right here I've got 4 paths, and so just follow back to the root. That might be a little easier. Okay, we don't use tree diagrams a lot because they can get messy fast. You know, we could have done a tree diagram here where at the first level we had 2 choices, head and tail, and the second level we had 6 choices. You know, and that ends up giving us 12 outcomes altogether. But these are our sample spaces. Okay? The sample space is the set of all possible outcomes, so the brackets indicate that it's a set. All right, so our first probability formulas, I am offering bonus points. Okay, I'm telling you about this now. All right, I really think you need to have a mental flow chart of all of the formulas that we're going to talk about. All right, and so you might want to put that mental flow chart on a piece of paper just to make sure you've thought about it. So we'll talk about several formulas as we're going through this chapter. You need to be building that flow chart, and you're going to submit that to me. You can do it on a piece of paper. You can go and do it on the beach and take a picture of it. You can use some online technology tool to come up with a, you know, I'm sure there's somebody in here who's into flow charts. Y'all know what a flow chart is. But we want to think about how we'll approach the formulas, and I'll try to get to a little bit of that, give you a demonstration of where we should be with our flow chart before we leave here today. I don't think no, it's not in Excel, but there's a tool called Prezi. That's a good one. There's also Spicy Node. That's a good one, and Mindomo. Those things really are kind of what they call mind mapping tools, where you can build an idea and here's the other ideas and other ideas. There are tools online that you can use to do it. But I don't want you to get bogged down in the technology. I really want you to know when to use these rules. Okay? So somehow you will have to submit that to me by the time you take the test. Okay? All right. So first 2 formulas. Really, these 2 formulas are the same. The only difference between them is where the data comes from. Okay? When we calculate probabilities based on relative frequency approach, we actually have some kind of observation or experiment. Okay? Versus when we deal with this classical approach, that's when we use the sample space. Okay, which is not how things work all the time. those are the possibilities, but that's not how things come out. Just because the probability of tossing a coin might be, or tossing a coin and getting a head might be 50%, does not mean when we toss the coin 10 times we're going to get 5 heads and 5 tails. That's not how it works. Okay, so relative frequency approach, the probability here of an event A or E or whatever, okay, is equal to the number of times A occurs, or let's say A is observed, divided by the total number of trials. Okay, that's what we did this morning or this afternoon with our coin tosses, right? We had some data, we had an observation, and we found that the probability of heads was the number of heads that we observed, which was 142, and we divided that by 250. We had 142 heads out of 250 trials altogether, and we came up with approximately 0.56 or 56%. Okay, that's what we call relative frequency probability. All right, versus classical approach. Okay, again, the data comes from the sample space. The probability of A is the number of outcomes over the total number of outcomes. And again, this is based on the sample space. So in theory, when we look at the sample space of tossing a single coin, it's heads and tails. That's it. That's the entire sample space. How many of these outcomes result in a head? No, when we do it from the sample space, just one, right? Only one. And how many outcomes are there altogether? 2. So that's where that 1/2 comes from. All right. But basically, it's the same thing. How many times did heads how many times did we observe it, or how many times does it occur in our sample space in theory, divided by the total number of trials or outcomes? All right. So I would not spend a whole bunch of time trying to distinguish between these two. Okay. Sometimes we calculate from data that we've observed, and sometimes we do it in theory. Okay, we'll talk a little bit more about that in just 2 seconds, but subjective probabilities, these are probabilities based on knowledge, all right, not necessarily data. For instance, you go to your doctor, and he talks about likelihood of you recovering from a particular illness or whatever. He's got some knowledge about that. He may not have actually ever sat down and calculated anything, but just based on his experience, he has some knowledge. And of course, people talk about probabilities all the time who have no knowledge, and that'd be subjective and wrong. And we won't go into details about that now. So just based on knowledge. The law of large numbers. That's not where I want to be. The law of large numbers is a theory that brings together the relative frequency value and the classical value. Basically, it says the more times that an experiment is repeated, the more times an experiment is repeated, the closer the relative frequency gets to the classical probability. Okay, so that's why we got a better estimate about what we believe the true proportion of heads should be once we put all of our coin tosses together. Does that make sense? That's why we got a better estimate of what we believe the true proportion of heads should be when we put our tosses together versus when we did them individually. Individually, when we looked at our data, I think we may have had some values that were as low as 3. You know, and
This
then we had
just talks
some
about-
as high
when we
as
talk
what?
about probability,
8 was very high.
It will not tell
But
you what's going to happen in the next outcome.
Okay, you can't use it to predict what's going to happen tomorrow. Probability is based on long run effects. So, you know, if we, like I said, we toss a coin 10 times, we're not going to get 5 heads, 5 tails. If we toss it 1,000 times, it's going to be very close to 50% heads. And the more times we toss it, then the better we should expect those results to be. What does that relate to that you all have to turn in very soon? Nope. Something else. You're already working on it. Very, very soon. Yeah, like today. The M&M thing, okay? With your M&Ms in the individual bag, there's no guarantee that it's going to reflect what the company says. But when we put our thousands of M&Ms together, that should come very close to what they have, okay? So that's what the law of large numbers tells us. I think we got that one now. Okay, moving on. In a survey of 1,100 female adults, 18 years of age or older, it was determined that 341 volunteered at least once in the past year. What is the probability that a randomly selected adult female volunteered at least once in the past year? Okay, first thing, before we even answer this, I want you to tell me whether or not you think this is relative frequency or classic probability. Okay, relative frequency, because it's based on what? Observation. Even though, you know, we might tend to think classical is better, sometimes relative frequency is all we've got. If we can't put our hands on essentially the population or the sample space, then it's pretty hard for us to say, you know, how many outcomes result in a particular thing. So we have to do relative frequency. So the probability of volunteer is going to be the number that volunteered divided by the total number surveyed. Okay. Okay. We get what? What's the top number? 341 over, okay, 1100, and we get what? Okay, 0.31 exactly. Okay. You sure? Okay. All right. That's okay. That's good. All right. So 0.31 or 31%. Okay. Do I care about fractions, decimals, or percentages? No. All of this says the same thing to me. What's most important is that you be able to recognize your answer among the choices on the test. Okay. So otherwise I really have no preference. Okay. Also, as we're doing this, don't jump too fast to the numbers. We'll be giving you some tools. These are the things you're going to build that flow chart with, and you want to use those tools. That's what the test is really about, not just these, you know, individual questions. So think about which rule applies, and so I wrote it out. You don't have to write it out, but you do need to think about it. Okay. All right. Next question. The local golf sells an onion bag, this AN, that contains 80 experienced golf balls. Suppose the bag contains 35 Titleists, 25 Max Flies, and 20 Top Flights. What is the probability that a randomly selected golf ball is a Titleist? And first let's answer what type of probability is used here. What kind? Classical. Okay, this is classical probability. Classical probability kind of starts with the knowledge of the population. We know what's in the bag. Okay, if this was relative frequency, what we would have to do is sit there and randomly draw out some balls and then look to see how many we got of each type over the total number that we observe. But this is classical because it's based on everything that's in the bag, the entire sample space. And so we would say probability of Titleists is going to be the number of Titleists divided by total number. Okay, so we had how many? 35 over 80, or what is that? Okay, 0.44 or 44%. Okay, very good. Okay. And we could do B. What is the probability that a randomly selected golf ball is top flight? How many top flights? 20 over 80, so that looks like 0.25 or 25%. Okay. Questions about that? Okay. Yes. The first one we said was relative frequency. And the second one is classical. All right, we have here what's called a contingency table. We like to summarize data in contingency tables in statistics. Basically, a contingency table allows us to sort our data by multiple levels. So in addition to, does it tell us how many people this is? Okay, we won't worry about that right now. It sorts them by whether or not they've used drugs, and then by whether or not they tested positive or negative for drug use. Okay, so this is a contingency table. The author brings up a couple of interesting points about tests where you can get a false positive or a false negative. A false positive means that the test indicates that you're positive for whatever the situation is here, drug use, when in actuality you've not used drugs. Okay, that can happen. False negative is it indicates that you did not use drugs when you did. Okay, the terms for that, and I should look this up, are sensitivity and specificity of the test. I can't remember which one is which, but those are important things when we design tests, because either way it could be a bad situation. Okay, but what we want to know is we want to find the probability of selecting someone who got a result that is a false positive. Okay, who would suffer from a false positive result? So we got the probability of false positive. We're going to look to see what up top, how many. Okay, number of false positives, which is what? Okay. And we're going to divide that by the total number. Okay. Comes up to, if you add all of them up, it comes up to 1,000. Okay. So that would come up to 1,000. 0.09 or 9%. Okay, questions about that? We added all of the values. When we add all of them up, it comes up to 1,000. Okay? All right, find the probability of selecting someone who does not use drugs. Is the result close to the probability of 0.866 for a negative result? Okay? So how would we do that? We're interested in probability of non-user. So we're going to look at what? It doesn't really talk anything about the test, just whether or not they use, or in this case, that they don't use. Let's, all the people here, okay, we want all of these people. All of these people are non-users. So we want to write it down and think about it. We want number of non-users. Users divided by total. Okay? And so the number of non-users is 950. We're going to divide that by our total of 1,000, and so we get 0.95, or 95% of the people in this screening are actually non-users. Okay, is that close to 0.866 for a negative result? Not close enough, is it? No, I wouldn't feel good about having to take that test, you know, because it only shows that 86% of the people get a negative result. Okay, and then imagine that some of those actually were users, so that even increases more the chance of a person with a. It's not a good situation. So whatever. But for now, we'll come back and talk a little bit more about that. But this is our basic probability formula. Okay. All right. For a family of 3 children, find the probability of having at least 2 girls. Okay, well, one way we would solve this is to write out the sample space for 3 children. Okay, and this is one that we'll talk about a good bit. That's an S. So you want to, be able to put a handle on this. And it could be, the nice thing about this example is we've got 2 outcomes, 2 possible outcomes at each level. Boy, girl, we could be talking about 0, 1. We could be talking about heads, tails. It's the same sample space, just change whatever it is we're using. Okay? So be comfortable with doing that. But I won't take the time to do the entire tree diagram. I'll just write it out. We could have boy, 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 girl, boy, girl, boy, boy, girl, girl, then girl, boy, boy, girl, boy, girl, 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 boy, and then girl, girl, girl. Okay, that's it. All right, and I knew when I started this that I should be expecting 8 outcomes. We'll talk about this a little bit later, but that's what we call the fundamental counting rule. It says if I have one event that can occur in M ways, and another event that can occur in N ways, and another one that can occur in whatever many ways it can occur, the number of ways that they can occur together is M times N times whatever else. So here my events are having children. How many ways can you have that first child? 2 and 2 and 2, which equals 8. And so that's how we get the 8 outcomes here. All right, that's going to be really important to us. Counting is going to be very important to us. We're going to talk about a lot of things. Okay, but we're interested in the probability of having at least 2 girls. Okay, so what are we going to look at? The number of outcomes with 2 or more girls divided by the total number of outcomes. So how many outcomes have 2 or more girls? Okay, 4. Very good. All right, they are 1, 2, 3, 4. At least. It's a small little thing, but in probability, it's important. Okay, so we're going to have to pay attention to things like that. We've got 4 outcomes that have at least 2 girls. We have a total of 8. And so the outcome is 1/2. Okay? Questions about that? How does that relate back to our law of large numbers? If we were to go out and find hundreds or thousands of families that had exactly 3 children, and we said, okay, we're going to mark as a success those that have 2 or more girls, okay, we would expect that the ratio would be close to 50%. Okay? Questions about that? Okay, good. Possible values for probabilities. Probabilities range from 0 to 1. Probability of 0 means it is impossible. It cannot happen. Probability of 1 means it is certain. All right? There's a big difference between 0 and even a small chance. You know? Impossible is impossible. The lottery that happened the other day, it was impossible for me to win it. I didn't buy a ticket. Okay? But if you bought a ticket, there's at least a possibility. It wasn't a large possibility. In that case, we would say it might be unlikely that you're going to win, but it was possible. Okay? So, you know, even though the numbers are different, impossible is impossible. It's not going to happen. And I'm going to leave that at that. Okay. And again, we say an event is considered to be unlikely if it has a small probability, and commonly we say a 5% chance or less is pretty unlikely. By the way, let's give the weatherman a break. You know, when they say there's a 40% chance of rain, that's based on relative frequency. They look at days that have similar characteristics with, I don't know, what they might look at, the humidity, air pressure, that kind of thing. And what that means is in 40% of those days, it rained. Which means in 60% of those days, it didn't. Okay? So you very rarely hear him say 100% chance of rain. But if he does, it means when we've had days like this before and pressure just like this in the past, 100% chance of rain. So that's what we expect, but that still doesn't guarantee what's going to happen. Probability is not a prediction tool. Gives us some idea, but no certainty at all. Okay, so we have to be careful. I think I want to come back to this example because it proved challenging on yesterday. So we're going to come back to that next time.